As before, we start with review from last class. So last class, we saw how to deduce that the Möbius transformations of the extended complex plane form a group from the fact which we had already shown that the Möbius transformations of the complex projective line form a group. Right? Kind of, we just transported the knowledge we had, namely that Möb of P1C is a group, to Möb of C bar. Right? That's what we started, how we started. Then later on, we showed this the simple transitivity on triples of distinct points of C bar. That is, we showed that whenever we are given two triples of distinct points, two ordered triples of distinct points in C bar, there is exactly one Möbius transformation taking the first one to the first one, okay, the second one to the second one, and the third one to the third one, right? Where, of course, the first order triple is required to consist of three distinct points, and so is the second triple. But of course, there could be some overlap between this triple and this triple. That is allowed. Okay, then we showed that circles go to circles, that each Möbius transformation of C bar sends circles to circles. And this was based on two observations. Okay? One observation was that the standard examples, they all obviously send circles to circles. And second, there was a special Möbius transformation, namely Z goes to 1 over Z, right? Kind of, which is the Möbius transformation associated to this matrix. And we showed that one sends circles to circles by composing it, by pre-composing it and post-composing it with stereographic projection, right? So in order to show that this one sends circles to circles, it was enough to show that this composition sends circles to circles, right? Where this one is the unit sphere in R3, and these are stereographic projection and its inverse, and it's first. In order to show that this one sends circles to circles, it suffices to show that composition that you are seeing sends circles to circles, because stereographic projection sends circles to circles, right? And its inverse as well, which we had already shown. Okay, and we argued, we gave some evidence as to why this composition, right, sends circles to circles. It's because we showed evidence that it is the rotation of 180 degrees around the x-axis, right? And then I left as an exercise to that you indeed show that is the case, right? And that could be done by just following the formulas both of this one and of this one, right? Well, and the inverse of P. Okay, so that's how we, okay, and then finally what we saw is that every Möbius transformation is a composition of standard examples together with 1 goes to 1 over Z. Right? And hence every Möbius transformation sends circles to circles. Knowing that, and because every Möbius transformation of C bar is a self-homeomorphism of C bar, we know that then we can deduce that then whenever I'm given a disk in C bar, and recall that a disk is one of the two connected components of the complement of a circle in C bar in C bar, and that a circle in C bar is either a circle in C or a straight line union the point at infinity. So don't forget that. Okay, now I can deduce that disks go to disks simply because I know now that a circle always goes to a circle, and so the two connected components of the complement have to go to the two connected components of the complement, right? And we saw how to decide which one of the two combinatorially if what I'm given is the 3 points in my circle in the domain. Right? So and mainly and essentially one just has to decide to follow the clockwise direction, and then the clockwise direction tells me which one of the two disks in the codomain is the image of the one I'm trying to decide. Okay, so that's more or less it, right? And this simple transitivity of triples of distinct points actually was done very explicitly, right? I mean, we gave very explicit formulas, right, in all possible cases. As I stressed last time, this can actually be programmed. Okay, so now let me just go here to the homework, kind of just to tell you that this exercise from last class it has to be submitted next week. So it's here it's pick two explicit distinct points. So by that what I mean is kind of your favorite ones, right? I mean it's like I don't know, 3 plus 2i and 5 minus 7i, right? And then for those very explicit points, compute all the matrices that take such that the corresponding Möbius transformation takes one to the other from those you chose. Okay,